Okay, hello everyone. So today we're going to continue our conversation around concurrency control. So last week or on Tuesday, we looked at just the basic theory again. We looked at the definition, the formalization, the dependency graph, the wait for graph. We looked at the deadlock prevention and deadlock detection mechanism. And we ended the conversation around the multi-granularity locking and the benefit of having the hierarchy of locking as opposed to just limiting ourselves with record locking. So today, we're going to now relax one of the assumptions that we have made so far when it comes to serializability and just the way we consider our data. So we've been looking at a fixed data model or a fixed database. But what if our database is dynamic? What is the effect of that on serializability? And what do I mean by that is just if we go beyond just having a fixed set of objects, because explicitly one thing we do assume that there is read-write conflict. So there is a dynamism or there is a database adapting and changing based on the query. But one thing we haven't really paid attention to is the addition and removal of objects, and in particular, when we add objects. And so what are the effects of allowing the insertion? So let's take an example. So for example, we could have a transaction T1 that it wants to find the oldest sailor. So let's assume that we have this relation, we have this table that it has a list of sailors and each sailor has a rating, and also we keep track of the age of each sailor. So now if the first query or the first transaction wants to find the oldest sailor, and let's say with the rating 1, then what it could do, based on what we've discussed so far, it could go ahead and lock every single record, and it may also go ahead and lock all the pages containing those records. And everything is good. And it finds that the oldest sailor for rating 1 is age 71. Okay, so that sounds good so far, nothing strange. But now assume there's a second transaction. And this second transaction, once T1 is done, hasn't committed, but the second transaction starts. And the first operation of the second transaction is that T2 will insert a new sailor with a rating 1 with the age of 96. So what would happen right now at this point?
I would say T1 has like incomplete information because it hasn't been updated.
Absolutely, it does have an incomplete information, but more importantly, all the precaution that T1 has taken so far, which is to just lock the record that it has read to make sure nobody's going to update them, that did not save T1. Even though you have locked everything, but since this is a new insertion, someone can come and insert a new record and it doesn't violate any of the lock that T1 is holding. Therefore, so now the result that T1 is getting is actually incorrect because the oldest sailor is no longer 71, is actually 96. And that's something that completely T1 is oblivious to. It has no idea that this actually taken place. Situation can get even more interesting. Let's say now T2 also deletes the oldest sailor with rating 2. So let's say that's 80. So there's a sailor has a rating 2 and the age of 80, and T2 goes ahead and deletes that and commits. And now T1 continuing its read, and it wants to still find the oldest sailor. So then says, okay, I'm going to go ahead and lock all the sailor record with rating 2, and it finds that the oldest rating 2 sailor is age of 63. So then what happens is that T1 now does not see the T2 artifact of removing of AD. So it doesn't see that because T2 removed AD. So now the oldest age is 63. So in fact, that update of T2 is now visible to T1. However, the first update of T2, which is to add record 96, is not visible to T1. So, and of course, this is no longer serializable because T1 sees some updates of T2 and it doesn't see some updates of T2. So it only sees partially. And there's no way of running the T1 and T2 serializably such that the effect of T2 is only partially visible to T1. So of course, it's not serializable. And we cannot find it. It just simply cannot run these two transactions serially by only making their effect only partially visible. So what is it that is really happening here? And the challenge here is what is known as phantom, is that if you assume a fixed set of objects, then all our locking mechanism or all locking infrastructure using 2PL, whether strict 2PL or regular 2PL, will work. But as soon as we relax that assumption, saying that we're not just dealing with fixed set of objects that can be updated, and the only thing that we need to guard against is the read-write conflict over a fixed set of objects, and then we go ahead and introduce insert, and the problem gets a lot more interesting. So any thoughts of how to there are different ways of now addressing this problem. It's not a open problem, but can you think of a way of handling this? How could we guard against these unexpected phantom anomalies? For example, could we use the hierarchical locking in order to prevent this? The multi-granularity lock that we discussed. For example, what happened if T1 got a S-lock at table level of the Saylor table? Would this be sufficient to avoid these phantom problems? Well, if T1 gets a S-lock, and we know based on the hierarchical locking, T2 must also hold an intention lock and IX lock at the table. And we know that the S and IX are incompatible. So in fact, if T1 were to take an S lock, then T2 wouldn't have been able to be executed. So that does provide a really broad protection. Of course, the moment we start getting these stronger locks, then our concurrency is limited. Sure, it fixes the problem, but it could also just always execute things serially in the worst. I mean, that's one way we already know that solves every single concurrency problem, is to run things serially. But the point is, how do we maximize the concurrency by interleaving the operation and handling the read-write conflict, but also now handling these type of phantom. So sure, that's a solution, but that doesn't not necessarily be the most ideal solution. What else can you think of in order to overcome this challenge? Any other thoughts? Can you think of a use of an index to prevent these type of challenges? If I had an index on the rating What if I had an index on age? Could this be beneficial here? So let me give, so while you think about that, let's look at this again a little bit more, sort of formulating the problem while you're kind of thinking about it in the back of your head. So again, here the issue is that T1 implicitly assumes that it has locked all records of rating 1. So that's an assumption. Just because it's individually locked every record doesn't mean that it prevents new record being entered. So that's where the problem gets introduced. And as long as we have an assumption that no new records are being added, then we're good. But of course, we want to be able to allow insertion of records freely. So we need a mechanism to enforce this. And there are two ways that often have been considered. One is index locking and one is predicate locking. Of course, we can use these multi-granularity lock as well too, but the challenge with those is that it would really limit the concurrency. In fact, locking an index is, you can think of it as a predicate locking. If I locking the table, giving an S lock on a table essentially is a form of a predicate locking. It really says lock all the records of any rating. So it is a predicate, but it is a very strong one. So the question is, can we do this better? Can we extend our conflict serializability to guaranteed when the set of the objects that are fixed can also be sort of relax that assumption and allow them to new elements to be added or removed. So let's look at index locking. So how would the index locking look like? Assume if we have an index on the rating and we follow the index to access the rating, and we know when we insert a new record, we also, as part of that transaction, we need to go and update our indexes. So one we could envision is that one thing we can do is that from the index, we lock the index key of R equal 1, of rating equal 1. So that means anybody else that tries to insert a new record of rating 1, for example, adding a rating 1 of age 96, or removing a record of rating 1, they need to come and update this index, because the index needs to be up to date as part of the transaction. But if this key is locked, then that update will need to wait. Therefore, it will avoid the problem of phantom. And so again, if there is a dense index, and we can distinguish between two kinds of indices, one is dense and one's sparse. A dense index means for every key, there is an entry in the index. A sparse index is that not every keys are indexed. Generally, we have dense index. So sparse index is not really a common data structure. And so as long as we have a dense index, then we could, and if the query is to simply find the oldest sailor of rating 1, then that's an easy way. We simply lock the rating 1 entry on the index, and that will guarantee that no new record can be added to the index, which guarantees that no transaction that attempting to change or add a new record of rating 1 can complete. Their commit will either need to be delayed, or the whole transaction that is attempting that change needs to be aborted. Of course, there could be a challenge, is that the query could be give me the oldest sailor of rating 1, but in fact there are no sailor of rating 1. And so that's one way to handle that, is to lock the page that the entry R equal 1 is going to land in. And you could also think of it, the query could also be, doesn't have to be just tell me the index of rating 1, the oldest sailor rating 1. The query, for example, could say, give me the oldest sailor of having a rating between 1 to 3. Okay, so now if we have an entry in the index of rating 1, so there are some existing sailor with rating 1, and there are some existing sailor of rating 3, then if I were to just lock rating 1 and rating 3, then I'm not going to prevent an insertion of a rating 2 while my query is running. So in fact, that entire range or that entire page that would potentially going to have any of rating that could potentially be of interest to me needs to be locked. So if I locked a page that holds 1, 2, and 3, or I locked a page that holds 1 and 3, and I know that the 2 either needs to go to the page that is on 3 or needs to go to the page that is on 1, then I will also be preventing the insertion of the 2 into the index, which will help me to prevent that insertion of that phantom. So again, it's possible that just locking that particular key in the index is not sufficient because there could be a phantom in the index itself. So that's yet another thing that one needs to take care, sort of pay attention to. And in fact, in sort of traditional, they have a next key locking. So not only I lock R1, but I also lock the key that R1 is pointing to, which in this case, at the moment will be 3. So now R1 is pointing to the next key of R pointing to is 3. So I also lock what it's pointing to. Therefore, if somebody now wants to add a brand new rating 2, which never did existed, or maybe add a rating 1.5, which didn't existed at the time when we started that exploration and running that query, all of those will be prevented. So with the index locking, which is the most common mechanism in order to prevent phantom, we can address this issue, the non-serializability issue that we just raised. Any questions? So let me make a pause here, see if anyone has any question. Again, to summarize, go on.
Oh, yeah, Professor. So we're not locking the whole index. We're just locking a few values inside the index, right?
Exactly. We're just locking, for example, the entry because the index has a key. The key of this index is rating. So, and this rating could be from 1 to 1,000,000. And if you're only, our query is interested to find the oldest sailor with rating 1, then we're just locking rating 1. If the index is, if the query is interested to lock index from rating 1 to 3, then we're just locking 1 to 3.
Okay, thank you, Professor.
Thank you. And if all, go on.
I was just going to say, this is like assuming that the index is like a page within the buffer pool. Then we do the locking on those pages of the index.
So the assumption we're making here is, first of all, there is an index on rating. Because if there's no index on the rating, then this solution won't work. And if there's no index on rating, then we may have to kind of go back to that broad solution of just locking the table with an S lock. But whether or not it exists in the buffer pool or not, that's the second important question. So as far as the data is concerned, or as far as the index concerned, everything is on disk. So if it's not in a buffer pool, so it's brought into the buffer pool. And also the actual a flag of marking that this thing is locked may or may not be added to the page of the index itself. You may have some external data structure that keep track of that. So you may just maintain a secondary structure that says, okay, rating 1 is now locked. So it doesn't mean that it has to be part of the index itself. And that's kind of lead us to the next potential solution of this problem, which is predicate locking. So we could formulate this predicate is that rating greater than 1 or rating equal 1 or age has to be, for example, twice the salary. So we can define this predicate. So whatever predicate that is being used for the reading, which in that case would be rating equal 1 or rating equal 1 to 3, we keep maintaining a list of these predicates. And we make sure that, first of all, these lists of predicates that we are maintaining are non-conflicting, but also when a new insertion comes or a new deletion comes, we make sure that it does not intersect with any of these predicates that are maintaining. So essentially, just the database continuously maintain a set of predicates. Rating is equal 1, rating is equal 5 to 7, or rating is 5 times the age. It doesn't matter if that makes sense or not, it's still a predicate. Now, if I want to add a new sailor and it has a rating 17, as long as that 17 does not satisfy any of those predicates, then it's okay for me to proceed and insert that 17, because it's not going to create any phantom or introduce any phantom for any of these queries that are currently running. So this problem of the predicate locking, it's kind of an interesting one, which folks started looking at it in the 90s. And now the interesting thing about the predicate locking is, what if there's a lot of these predicates? I mean, if I have a lot of concurrent query running, then there's a lot of predicates. Now the question is, well, how do I speed up checking whether what I need to insert or what I need to delete or the operation that I need to do has any conflict with the existing set of predicates? Then you need to scan these predicates faster. Then, so one way to do that, then we say, okay, then let's go index are these predicates. So now given a query, given an index set of predicate, can I quickly find if what I'm trying to do intersect or overlap with any of the holding predicates? So then there's a whole interesting field kind of emerged from this. And in fact, some of the work that I did for my PhD, I looked at this problem, is that this predicate can be seen as an object in a high dimensional space. And now really the problem turns into indexing, high dimensional space indexing. So given an object, given insertion, for example, I search in this high dimensional space and kind of see whether it intersects or whether it is contained in any of the existing ranges, these predicates. And each predicate can be visualized as an n-dimensional object. So that's so there's lots of work on that front. The other thing you may heard about is publish subscribe system, or even like your RSS feed, which was, I guess, popular in the early 2000s or late 90s. So the problem there is that, or the publish subscribe paradigm is that you have a set of subscriber and you have a set of publisher. A subscriber says what are they interested in. Publisher says, well, publish is an element. These subscribers essentially can be formulated as a set of predicate, and the publisher is they are putting out an article. If that article matches those preferences, those predicates, then it will be sent to those subscribers. So, and this is a very sort of an abstract paradigm that pops up, which again has lots of application within computer science, and especially as middleware. So again, all of those problems can be reduced to this simple problem of matching or predicate matching predicates. This matching problem, and the problem in all of them is that you would have a large set of predicate, and how do you index these predicate? So far, our indexing has been just on indexing data, but now extending that to indexing Boolean functions, or just predicates in general, arbitrary predicates potentially. Any question? Okay. So that's first part. Again, looking at the concurrency theory, looking more precisely at two-phase locking, that pessimistic approach, looking at the detection and prevention method of deadlock, looking at the multi-granularity locking that allows more efficient usage of locks, especially when we have queries that needs to access a large part of the data, as opposed to getting too many individual locks. Can we get these higher level locks? And then we finally looked at the problem of phantom, is that if we no longer assume our databases consist of set of fixed objects and we allow insertion, then how do we prevent this phantom? Is that I locked a record, I cannot lock what I haven't seen, so how do I deal with that? So we looked at index locking and the predicate locking. Now let's kind of expand our concurrency control, and let's look at one of the very first optimistic concurrency control that was, I believe, from late 70s and 80s. And we've already seen flavors of optimistic. So 2VCC is an optimistic concurrency control. So now what I'd like you to do as we're going over, actually, we're going to cover three things. We're going to look at optimistic, we're going to look at time stuff, and then we're going to look at multi-version concurrency control today. And a lot of these elements that we're going to cover, I want you to see if you can draw back to what we discussed so far with regards to 2VCC and Outstar, and especially the multi-versioning architecture that we have in Outstar. So there is going to be a lot of parallel. Of course, every time a new piece of work comes out, you really build upon what has been done. And I think this is a good example of seeing different elements are taken from different piece of work and innovatively with new ideas, kind of a new piece of work has been created. So I think that's something important to pay attention to as we go throughout these slides. So again, locking is conservative, something we've touched upon already, and it is considered pessimistic. And so it's one way to prevent conflict, as we've discussed, but there are disadvantages. Main disadvantage is the necessity of maintaining a lock management and its overhead. And we've talked about how crucial it is to have a really finely optimized implementation of the lock manager. Otherwise, the performance is going to deteriorate very quickly. And companies have spent millions and tens of people over the years, 20, 30 years span time to really optimize the construction of these lock manager. Of course, then we also have to deal with the deadlocks. And we also need to deal with the contention. If there is a one single record that everybody's interested and we continuously try to lock it, there's going to create additional contention. Of course, we looked at a completely lock-free design, and in a sense, a concurrency control-free design of Quick that does prevent many of these. But let's look at sort of a classical approach that handle these. And the kind of idea of the optimistic CC, at least from the classical perspective, it says if the conflicts are rare, then maybe we don't need to be so conservative in the way we access the data. Maybe we can go ahead and access it and then later ensure that what we read is still valid, and if so, then commit transaction. Of course, when we look at least modern concurrency control running on in-memory databases with lots of parallelism, If there are no conflicts, or if the conflicts are rare, experiment results shows that it doesn't really matter which technique you use, whether you use optimistic or pessimistic. The margin of difference is very small. It only becomes interesting when you actually have conflict, and how do you allow execution under contention. So I think that's the sort of the interesting aspect of the space comes into play. But let's look at this Kung and Robinson model, which was one of the very first proposal of to do optimistic concurrency. So the idea starts is that this is a transaction. It's kind of the current, or this is the root of the data, and it's currently pointing to two data items. Okay. So the transaction has three phases. So there is a read phase in which the data is read and private copies of the objects are made. There is a validation phase. We check for conflicts. And then finally is a write phase, which we make our local copies of changes public. So for example, if currently these are the blue and the red are data objects, and from somehow we can get to access to these blue and red object, we can think of is that if we have another transaction that is modifying it, we create a local copy with empty space is shown. It's just it's no longer filled with blue and red. These are the new copies are made, and the new copies are made. And once they are completed, then we swap the pointer. So instead of pointing to the old structure that was pointing to the initial value, then we point to the new object from which we can get access to the new value. So essentially a form of a pointer swap. I mean, this is a very abstract view of this, but the idea is you had the old data. When you go ahead and you run your transaction, you write your local copy, and once your transaction is ready to commit, it gets validated to be committed. Now, for example, the page directory or the index, instead of pointing to the old value, now they can point to the new value. That's the basic idea. And in terms of kind of now relating back to what we discussed, first of all, for example, in LStore, we also have this notion of having an old copy or a new copy. So for example, if the record has been updated, the indirection is pointing to the old copy. Writing a new tail record and then making the indirection point to the new tail record is essentially an implementation of this idea. Here, there's no actual implementation. It's just an abstract idea, but that the LStore, in fact, is an efficient way of providing an implementation to this abstract idea. The other thing sort of drawn attention to, this notion of the validation phase can be seen in the 2VCC, for example, as a certification. You go ahead and read all of your data. In fact, the way, for example, we talked about in LStore is that we go ahead and write the tail record, and the tail record is visible to everyone. But whoever is reading it knows that this tail record is still uncommitted. And at the time of the commit, we're just marking the transaction who wrote them as committed. So therefore, any reader can now go ahead and read those records. So again, that's not only the validation, it can be mapped to 2VCC as a certification phase, but in fact, we could map it of the right as the idea of holding that update log and update intent log. And so we go ahead and actually write the tail record, but we just tell all the ongoing transaction, all the concurrent transaction, that the transaction who's written this particular tail record is still not committed. So you can go ahead and read it, but you're going to be reading uncommitted data. So again, every aspect of this sort of basic optimistic design, there is a mapping to it, to the way we do things in Elstor, and to the way things we've been sort of discussing over the past few weeks. So any question? Again, very basic model. You first read, then you validate what you read. And if the validation succeeds, then you go make your write visible. Your local copies becomes the sort of the global copies. Let's look at what the validation entails. And again, the validation here is rather simplified validation method. So to test the condition, to ensure that there's no conflict, the way we construct, each transaction is assigned a numeric ID, which could just be the timestamp. And these transaction ID are assigned at the end of the read phase, just before the validation begins. In other words, we can think of these transaction IDs are assigned at the beginning of the certification phase. And why then? I'll let you kind of ponder upon that. Why can't we assign them earlier? I mean, you can assign them earlier. There's nothing that prevents it. But if you were to assign it earlier, you need to think about, would it cause a potential, for example, if my validation takes, if my read is taking a long time, then would that cause, if I were to assign that ID much earlier on, would that cause triggering more invalidation and more abort? So that becomes an optimization question as well too, whether it makes sense to assign that ID at the time of the read or at the time of the certification. And in general, we talk about a read set and the write set. The read set is a set of objects read by the transaction. The write set is a set of objects that is going to be modified by that transaction. Now let's look at the rules of the validation. So we have two transactions, TI and TJ, and they have the three phases that we talked about. There is read, there is validation, and then there is write, TI and TJ. Now, so this is, and the way we do this, we're gonna run these set of tests. So for all I and J, for any two transactions, if the TI and TJ, so if the TI is before TJ, that means the assigned timestamp of TI at the beginning of the validation is less than TJ, then as long as TI completely ends before TJ starts, that means the end of the write set of TI does not overlap with the read set of TJ, then trivially there is no conflict between these two transactions. So for any I, or for any J that is bigger than TI, if TJ is completely starts after TI completely ends, then there's clearly no conflict between the two. So now a second test. Now assume that TJ and TI, there is some overlaps among them. So now again, for all TI and TJ, where TI is smaller than TJ, meaning that the validation of TI starts before the validation of TJ. So as long as the TI completes before the TJ begins its write set. So that's important. So this condition needs to be met. So what this means is TI completes before TJ begins its write set. In other words, anything that TJ writes, it's not going to interfere with, or it's not going to overwrite TI writes, and it's also not going to invalidate what TI has written. So as long as TI completes before TJ, its write phase, so definitely we've kind of eliminating all those potential anomalies. So the only anomalies that is left is that what if what is TI is writing overlaps with what TJ is reading. So it's possible that TJ, depending on when those reads are done, they see some of these updates and they may not see all of them. For example, let's say what is TI is writing is identical to what TJ is reading. Since TJ read started kind of slightly earlier before making the TI writes visible, it's possible that only half of these writes are seen and half of these writes we haven't seen. So that will violate our serializability. So the basic condition that was introduced in the Cohen-Robinson was, as long as these two sets are non-overlapping, then we're good. Sure, it's a very coarse condition, but it is correct. So all it says is that this TJ write set, the write of TJ, it's only become visible once TI is completely done. That means there is no conflict between the write set of TJ with anything that TI does. So that's perfect. That's easy. That's an easy rule. The other says, okay, and if you were to overlap the read and write of TI and TJ, then we make a very coarse assumption or requirement that this read and write that is happening concurrently should have zero overlap. Okay, so if there's no overlap between read and write here, and all the writes of TJ is done after TI is completely done, then we know that, well, these two are not conflicting. So it shouldn't violate the validation. Because first of all, we know that TJ is not reading any dirty data, because it would have been reading a dirty data if we were kind of reading this partially, but that's not the case. There's no conflict after this transaction is fully committed, or in fact, since there's no conflict, this is trivially satisfied. TJ is not reading any dirty data. Let's just make it even simpler, because what TI is writing has no overlap with what TJ is reading. So it's trivially satisfied. And TI overwrites TJ writes. While TI is kind of done, these writes are done completely before even the TJ write starts. So again, we're never going to get that condition as well. So again, it's a very coarse set of rules, but of course, if these coarse set of rules are satisfied based on the Robinson and Cohen-Robinson model, then this validation also passes. So the final test, now if we kind of really overlaps TI and TJ, again, the only thing it says, the validation of TI is starting before validation of TJ. And the reason we're making that assumption is because this becomes the timestamp, because we want to say TI is smaller than TJ. We're not going to have two transactions at the same timestamp. This is monotonically increasing timestamp when we assign. So either must be TI is smaller than TJ or TJ is smaller than TI. But anyhow, so assume that TI is smaller than TJ, but we have no, there's nothing, all of these could happen. The reads are happening concurrently, the validations are happening concurrently, and the writes are happening concurrently. So we have there's no mechanism of coordinating that concurrent execution. So now what other rules do we need, or what other test needs to be done? So first of all, TI completes read phase before TJ does. So that means the validation of TI starts before the validation of TJ, which goes back to the point that the assumption we made that TI is smaller than TJ. So that's basically this first criteria. But now this becomes kind of a little more interesting. We're saying now the write set of TI does not overlap with the read set of TJ. And that's something we said it before too. Since the write is happening potentially at the same time as the read is happening, or the write is happening either at the same time, or the write is happening after the read is done, completely invalidating what was read, or completely invalidating the repeatability of what was read by TJ. Well, the simple rule that the Robinson and Cohen says, well, we assume this test is passed if this write set doesn't overlap with this read. Okay, so that seems pretty coarse and makes sense. If there basically says if these two are not conflicting, then it should be okay. And the other thing that is also adding is that the write set also must be non-conflicting. So the only thing that could potentially conflict is the read set of TI and the write set of TJ. That's the only thing that is being allowed. But since this writes we know already happens once the read is completed, they're already being sequenced. And so by that construction, that's also being taken care of. So they're very coarse. I mean, these are very coarse conditions, but of course, they're kind of intuitive in a sense. If these are two concurrent transactions that either there's no conflicting operation among them, or if there is conflicting operation, potential conflicting operations, such as the read of TI and the read of the TJ, if we strictly ordering them, meaning that this read ends before this write starts, so there's a strict ordering between the this potential read-write conflict, and everything else is conflict-free, then it's kind of easy to see that, well, it's okay if these transactions optimistically are ran together. Or if they do run concurrently, they don't violate the serializability criteria. So that kind of sums up sort of the basis of the optimistic concurrency control of Kung and Robinson, which is really the first sort of formal optimistic concurrency control that was proposed in the database community field. Of course, nobody, I don't think, has really implemented this. This is kind of not the most efficient way of, there's too many things you need to maintain, and the conditions are coarse, so it's not going to be really performant, but nevertheless, it's it is the first one. So it is interesting and innovative from that perspective. So one thing one needs to do is this validation needs to be a critical section. So the validation and the write phase has to be in a critical section. Nothing can happen concurrently. So that's another sort of a drawback of the model. And if the write phase is long, or if the validation takes long, that means the entire database is not executing single threaded. So again, that's also won't be performant. And you could optimize for read-only transactions. So if the transaction we know ahead of time a priori is read-only, then we could run the read-only transaction without having any critical section, because there's no write phase involved in it. But overall, I mean, again, it's an interesting, just from the sort of the historical perspective. Any question on this optimistic design? So the basic idea is you have read, write, you have read, validate, and write. And if there are any conflicting or if any concurrent execution, we have to make sure that the write set of the first transaction does not interfere with the read set of the following transaction. And if they are really interleaved, then we also need to ensure that, in addition to ensuring that the write set of the first transaction doesn't interfere with the read set of the next transaction, but also the write set of the first doesn't interfere or doesn't conflict with the write set of the second. So basically eliminating all potential conflict. The only thing that we are allowing to happen is that the write set, the read set of the first and the write set of the second transaction could have potential conflict. But since you're saying they're strictly done non-concurrently, those two, then everything is okay. So that's the kind of the intuition behind this optimistic model. Any question? Okay. And there's other overhead to this as well, is that we need, again, we also need to maintain all the read and write set of every transaction, but that's less of a concern. A lot of different concurrency protocol may require the maintaining of the read and write set. And in fact, when you're implementing it, you have your transaction object. Your transaction object most likely will have your read and write set too. So that's not a huge requirement. And I think it's something that almost every concurrency protocol or most implementation will maintain anyway. And destroying or removing this object is also not a short, it is a task, but it's not a crucial one, or it's not a really expensive one, because these are local read write set or local to that transaction object. So it's not that other transaction or other thread are accessing it. So its removal is also and not a major task as well. But of course, it is nevertheless, it is the overhead that needs to be taken care of. But one key distinction, to kind of draw it back to the 2VCC model and the right certification and the certification process. The certification that we talked about in 2VCC doesn't have to be run in a critical section, versus the validation here needs to happen in the critical section, meaning that there's only one validation happening at a time, versus in the 2VCC, many validation could happen at a time. And the reason for that, for this crucial difference, is that since in the certification that we talked about, the way the certification process works is that we're locking the record that we need to access. Then whatever we locked, we know no one can touch. Versus here, there's no locking involved. So if I validate my first record that I can validate, if I validate my first write, by the time I come to my validating of the second write, someone else may have now violated that first one or read that one or whatever may have already have happened if there's no locking. So since I need to validate a number of things, and if I don't have the ability to lock things, then that entire validation needs to happen in a critical section, meaning I lock everything. Versus in the certification phase of the 2VCC, we had essentially fine-grained locking. As opposed to lock everything and do the validation, we individually locked all the items that we validated. So you can think of that was a fine-grained locking, just locking everything that was validated as we go along, versus in the Robinson and Kuhn model it's a very coarse locking. We don't have fine-grained locking, so we just say we lock everything when we do the validation, or the entire validation is happening single-threaded in a critical section. Any question? And the optimistic CC, of course, like any other concurrency control, if a transaction fails in the validation, you could choose to restart it or just tell the user it failed. And the optimistic 2PL, the two-phase locking, which is analogous to 2VCC, is that we can always get shared locks as usual and make changes to the private copies of the object, but then obtain the X locks at the end of the transaction before making the writes global. So that's an idea that's very similar to what we talk about in terms of a 2VCC. And in contrast to both the optimistic CC or the Kuhn-Robinson, this approach doesn't require that validation phase to be done, doesn't require the validation phase to be done in a critical section. But then it does, as we talked about before, even with 2VCC, does involve the need of waiting for locks and potentially even dealing with deadlocks. So doing the validation by holding individual locks as you do the validation versus just doing the entire thing as a single critical section, the individual locks, of course, gives a greater degree of concurrency versus the, but then you have to deal with deadlocks versus the other model. Well, it's very coarse. It's only one thing has happening. Well, of course, there's no deadlock, but also because the concurrency has essentially been eliminated since one thing is running in the critical section. Any questions? So let's look at another variant of concurrency. Again, these are all really the classical method, is timestamp. Again, there are some, and there's some similarity to the outstore model as well too. So the basic idea is, given each object a read timestamp. So now every object or every record in the database has a read timestamp, and it has also a write timestamp. The write timestamp is basically the timestamp of a transaction that wrote the object, and the read timestamp is the timestamp of the transaction, the last transaction that read the object, or the transaction with the highest timestamp so far that has read the object. And when the transaction, so this is per record, so every record has the read and the write timestamp, and any transaction is also assigned the timestamp, and that timestamp is assigned or is generated when the transaction begins. We talked about in the optimistic one, the timestamp was being generated at the time of the validation phase. But here, the timestamp is generated at the start. There are two ways typically timestamps are generated either at the start, either at the validation time, or at commit time. So those are the different points in time that one will generate the timestamp. You can always typically do the timestamp always at the beginning, but then that may not be the most optimal choice in terms of the abort and invalidation rate that one may get. So the basic idea of the timestamp concurrency is this basic statement is that if I have two transactions, Ti and Tj, and Ai is the action of Ti and Aj is the action of Tj, and I do have the timestamp such that the Ti timestamp is before Tj, then basically I just need to make sure the action of Ti is before the action of Tj. If this rule is satisfied, then everything is good. Otherwise, it violates and the transaction needs to be aborted. In other words, is that in the normal concurrency control, like a 2PL, we don't have a predetermined notion of which transaction needs to be first. The determination of which transaction is going to appear before some other transaction is just by the nature of the way the locking, the scheduled, or the non-determinism that led to the way these different transactions acquired their locks. But in the timestamp model, when the transaction starts, at that point in time, it's given a timestamp. So that ordering is predetermined at the start of the execution. So the only thing to ensure serializability that we need to ensure is that since we already given a predetermined order of how these transaction needs to be scheduled, or the operation of this transaction needs to be scheduled, so the only thing that we need to ensure, if there are conflicting transactions between any pair of transactions, then those operations must follow the timestamp order. The operation of Ti must always be done. The conflicting operation of Ti must always be done before Tj. So that's sort of the basic rule. So now let's look at how the read works. So we're going to look at how the read works, and then we're going to look at how the write works to implement this this criteria that we just laid forth. So now the question is a transaction T wants to read an object O, wants to read the record O. So now if the timestamp of T is smaller than the write timestamp of O, what does that mean? Meaning that this timestamp, this transaction was before this object was written. So this object is written by a transaction who has a starting time of 5 p.m., let's say, but transaction T has a start time of 4 p.m. Therefore, an object that is written by a 5 p.m. transaction should not be visible to a transaction that was supposed to run at 4 p.m. So this will violate the ordering because this write should not be visible to this transaction because this write has a higher timestamp. The write timestamp of this is 5 p.m. The timestamp of this transaction is 4 p.m. So the only thing that should be visible to a 4 p.m. transaction is whatever was written before 4 p.m. Whatever was written after 4 p.m., which is in this case, let's say it was 5, it shouldn't be visible. So if a transaction, and again, we're not maintaining versions or anything, there's no multi-version here. There's just a single in-place update, and that update that we do, it has a read stamp and a timestamp, as a read timestamp and as a write timestamp. So now if, as you know, and also we're running things concurrently. So it is possible that the 4 p.m. transaction had to do so many different things, had to read so much amount of data, and finally it comes to this object that it needs to read, and it says, okay, this object was written by a transaction with the start time of 5 p.m., but I'm starting at 4 p.m. So this write should not be visible to me, and I don't have any way of reading what the previous value of this record was. The model doesn't assume that. It's a single version model. And simply that read cannot succeed. And so what the T needs to do, it needs to restart and it needs to run with a larger timestamp. If you remember, in order to deal with the deadlock ordering or with the lock ordering, to maintain the priority, when a transaction was given a timestamp, the older the transaction had a higher priority. So we maintain that priority. But in this case, when we run a transaction, restart the transaction, we always give it a new timestamp, because if you give it the original timestamp, well, if it invalidated the first time, for sure it's going to invalidate the second time because there's probably even more writes. So the retry always have to be with a new larger timestamp. So that's the first case. So if the first case is clear, if I'm reading an object that was written by a transaction that was predetermined order after me, then I can't read that. Then I should abort. So that's all this condition says. Now, what if the timestamp of this transaction is larger than the write timestamp? So again, go back to the same example. If the write timestamp was at 5 p.m., but the timestamp of this transaction is 6 p.m., well, then everything's good. Then I can go ahead and allow the read. Then what I also need to maintain is that, because as we said, every object needs to have a read set, a read timestamp. And now the read timestamp of O is going to be set to this new 6 p.m. Of course, if the read timestamp of O is already 7 p.m. because even a newer transaction is read, we're not going to modify it. We're just keeping the maximum or the delay. We're going to keep the value of the youngest transaction or the newest transaction that has read the object. So the read as part of the read, whenever read is allowed, when the write is visible, the read is allowed. And when the read is allowed, the read timestamp of that object is also modified. Any question? Okay. And these read timestamp is also something that needs to be materialized to disk, because so that's important to avoid the violation of what was written and read. But that's kind of a side issue. So now so that's the read. If the write is not visible, the read is rejected. If the write is visible, the read is accepted, and the read timestamp of that object is updated. So two basic steps. So now let's look at what happens with the write. So when a transaction wants to write the object O. So if the timestamp is smaller than the read timestamp, that means there was a transaction with the timestamp of, let's say, take the example of 7 p.m. There was a transaction of timestamp 7 p.m. that read O. And this transaction that wants to write O has a timestamp of 5 p.m. So that means if it allowed this to go through, this write of this transaction at 5 p.m. should have been visible to the 7 p.m. transaction. That means we are going to invalidate that read, and we're also going to invalidate the repeatability. So if a transaction is already read by a newer, if an object has already been read by a newer transaction, an older transaction cannot override it. So that write will be aborted and rejected. Also, if the timestamp of a transaction that wants to write the object is smaller than the timestamp of the writer of the last transaction who wrote this object. So if the last transaction who wrote this object is at 6 p.m. and now I'm a transaction at 5 p.m. and I wanted to write to this object was already written by even a newer transaction at 6 p.m. So if I'm a 5 p.m. transaction, I cannot write it. So basically, if I'm trying to write something and that I'm trying to write to an object and that object has already been read by a newer transaction, it fails. If I am trying to write to an object and that object has been written by a newer transaction, it also fails. In other words, if I'm writing an object and that object has either been read or written by a newer transaction, my update will not go through. There is an exception to this rule, which is known as Thomas Wright rule, which says, consider this example on the bottom. T1 reading A, T1 also writing A. T2 is only writes A. And we know that the timestamp is generated at when the transaction starts. If this version that T2 is writing has not been read by anyone, meaning that this condition, the first condition is not going to happen, so it hasn't read by anyone, then we can make an exception. Since we say, okay, we allow this write to go through because this version, although it's earlier, since it hasn't been read by anyone, we're not going to violate anyone's repeatability read, then we can let it, we can safely ignore this outdated write and allow that write to go through. So that's kind of just an optimization. But the gist of the write, so the gist of the read was simple, is that I can only read something that is visible to me. And if I were able to read something that is visible to me, I should update its read timestamp of that record. And in terms of write, two simple conditions, which can be combined to one. I can only write if what I'm writing to has not been read by a newer transaction or has not been read by a newer writer. So basically all this says is that once I predetermine the order of the transaction, then any conflicting operations are strictly ordered by that assignment. So this makes sure that the writes are ordered, because I'm not going to overwrite something that's already read. I'm not going to overwrite something that is written. And in the previous one, I only read what is visible to me. If it's not visible to me, I abort. So all these conflicting operations, all the potential read and write conflict are strictly ordered. Any question?
Professor, could you repeat
Yes.
once again, when is it that we write?
When is it that we write? Sure. You're able to write is that the record that you're writing to has not been written by a newer transaction or has not been read by a newer transaction. So that means, so an example is that the transaction T here that wants to write, it has a timestamp of 5 p.m. Okay, and the object that it wants to read, the object that it wants to write to, it has already been read by a transaction that has a timestamp of 6 p.m. So I'm a writer. I want to write. I want to write the object O, which has a timestamp of 5 p.m. Okay. And if that transaction and if that object that I'm writing to has already been read by a transaction that was at 6 p.m., that means my write should have been visible to this to the other transaction had the write of 6 p.m. because mine is 5 p.m. This transaction who's read the current value of the object had the 6 p.m. Time. So that means any changes before 6 p.m. should have been visible to this transaction. But since this transaction hasn't read my update, hasn't seen my update, so if I now go ahead and try to update that, I'm going to invalidate the read that that transaction has done. So that's first thing. So invalidating what is already read by a newer transaction. So that's first condition. The second condition is if the current object has already been written by a new transaction. So again, I'm a 5 p.m. transaction, and the object that I want to write to has already been written by a transaction at 6 p.m. So my write cannot go over that because 6 p.m. should be the latest write. Cannot go back in time and say, okay, now this is overridden with the 5 p.m. So the 6 p.m. is already installed. So this 5 p.m. transaction can no longer modify it. So as long as those two are satisfied, then the write can go through. Does that help?
Got it.
Again, just two conditions.
So you're right when the timestamp for both reading and writing was before. You're right. So
yeah. So yes. So exactly.
Okay. Thank you.
You're welcome. Because if a transaction, the current object is 4 p.m. So the last transaction who read this object was at 4 p.m. and I'm now a 5 p.m. transaction. I'm modifying this, so my changes at 5 p.m. should not even be visible to the 4 p.m. transaction. So it's okay for me to go ahead and make that change. And also similar thing for the write. If the transaction was written at 4 p.m. and now I'm writing the next version of this next version of this record is at 5 p.m., which is logically after 4. Again, that's also fine. All right, so I think that's a good place to stop. We still have the multi-version concurrency, which again is a classical multi-version concurrency control. And again, there's some overlap and there's similarity between the else store and the multi-version, this classical multi-version concurrency. So we will cover that next week. So if you have no further question, have a wonderful day and have a wonderful weekend. And if you have a question, I'm more than happy to answer them.